What is certificate pinning? Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving into certificate pinning, a critical security technique that helps protect your applications from sophisticated man-in-the-middle attacks. A key question we will answer is exactly where the pinning information lives and how it differs between mobile apps, desktop apps, and web applications. Certificate pinning is a security mechanism where an application is configured to trust only specific certificates or public keys, rather than accepting any certificate signed by a trusted certificate authority. Normally, your browser or application trusts any certificate signed by one of the hundreds of certificate authorities installed on your system. With pinning, you explicitly tell your application to only trust certificates that match a specific fingerprint you have pre-configured. Let me walk you through the sequence diagram that illustrates how a man-in-the-middle attack works without certificate pinning. The attack begins when a mobile app attempts to connect to the real server. Instead of reaching the real server directly, the connection is intercepted by an attacker who is positioned in the network path, perhaps through a compromised Wi-Fi network or DNS poisoning. The attacker needs a certificate to present to the mobile app, so they request a fraudulent certificate from a compromised CA. This compromised certificate authority might be a CA that was hacked, a CA that was tricked into issuing a certificate through a validation flaw, or even a rogue CA that was improperly trusted. The compromised CA issues a fake certificate for the real server's domain and sends it back to the attacker. Now the attacker presents this fake certificate to the mobile app. The mobile app needs to validate this certificate, so it checks with the System Trust Store, which contains all the certificate authorities that the operating system trusts by default. The System Trust Store confirms the certificate is valid because it was legitimately signed by a CA in the Trust Store, even though that CA should not have issued it. With the fake certificate accepted, the mobile app establishes what it believes is a secure connection and sends sensitive data like login credentials or personal information to what it thinks is the real server. The attacker receives this data in plain text, can read or modify it, and then forwards the request to the real server using a legitimate connection. The real server responds to the attacker, who then forwards the response back to the mobile app. The user has no idea their data was intercepted. Certificate pinning breaks this attack chain by removing the implicit trust in the entire CA system and replacing it with explicit trust in specific, known certificates. But where exactly does this trust information lie? That depends entirely on what type of application you are building, which we will explore in the following slides. Mobile app pinning compiled into binary. Let us examine in detail how certificate pinning works for native mobile applications, where the pins are compiled directly into the application binary. The sequence diagram shows the complete lifecycle from development through runtime. Let me walk through each phase. During the development phase, the developer first obtains the server certificate from the production server. The developer then uses a tool like Open Secure Sockets Layer to extract the public key and compute its SHA-256 hash. This produces a base 64 encoded string that uniquely identifies the certificate. The developer adds this hash string to the app source code, typically in a configuration class or PLIST file for iOS, or in a network security config XML file for Android. During the build phase, the build system takes the source code containing the pin hashes and compiles it into the app binary. For iOS, this produces an IPA file. For Android, this produces an APK or AAB file. The pin hashes are now literally embedded in the compiled binary code. They are not in a separate file that can be easily modified. They are part of the executable itself. The App Store then distributes this binary to the user device. When the user installs the app, the binary containing the embedded pins is copied to their device. During the runtime phase, when the app needs to connect to the API server, it initiates a TLS connection. The API server presents its certificate. The app binary performs standard TLS validation first, checking the certificate chain against the device trust store. Then comes the pinning check. The app binary reads the pin hashes from its own compiled code, computes the hash of the received certificate, and compares them. If they match, the connection proceeds. If they do not match, the connection is rejected. The critical point is that the pins are read from the application binary itself, not from the server and not from any external source. The app is comparing the server certificate against values that were decided when the app was compiled and have been unchangeable since then. Web application pinning space browser controlled. Web application certificate pinning works fundamentally differently from mobile apps because you do not control the TLS connection. The browser handles all TLS connections, and your JavaScript code runs in a sandbox with no access to certificate validation. Let me walk through the diagram that shows how web application pinning was historically implemented and why it is problematic. The process begins with the server admin configuring the web server to send a special HTTP header. This header is called public key pins, and it contains the pin hashes along with a max age value specifying how long the browser should remember the pins. When a user browser makes its first HTTPS request to the web server, the TLS handshake happens first, handled entirely by the browser. After the secure connection is established, the web server sends the HTTP response, which includes the public key pins header containing the pin hashes. The browser extracts these pins from the header and stores them in its pin storage, which is a persistent storage area within the browser. The max age value tells the browser how long to keep these pins, often set to weeks or months. On subsequent visits, when the same browser connects to the same server, the browser retrieves the stored pins from its pin storage. During the TLS handshake, the browser validates the server certificate against these stored pins. If the certificate does not match the pins, the browser blocks the connection entirely and shows an error to the user. However, this approach has critical problems. First, there is a trust on first use vulnerability. The very first connection has no pins to validate against, so if an attacker intercepts that first connection, they can inject their own pins. Second, the risk of bricking your website is severe. If you lose your private key or make a configuration mistake, users who have cached your pins cannot connect to your site at all until the max age expires, which could be months. Due to these serious risks, all major browsers have deprecated and removed support for HTTP public key pinning. Chrome removed it in 2018, Firefox in 2019. This header-based approach is no longer a viable option for web applications. Pinning types comparison. Now that we understand where pins are stored for different application types, let us compare the three main approaches to what you actually pin: the full certificate, the public key, or the CA certificate. The first approach is full certificate pinning, where you pin the entire X.509 certificate. This means you store a hash of the complete certificate including the public key, issuer information, validity dates, and all extensions. Any change to any field causes the pin to fail. This includes certificate renewals even if you use the same key pair. The advantage is maximum security, but you must update your application every time the certificate changes, which could be annually or more frequently. The second approach is public key pinning, where you pin only the subject public key info. This is more flexible because you can renew your certificate with the same key pair and the pin continues to work, as long as you maintain the same private key on your server. Certificate renewals do not require application updates. This is the recommended approach for most applications. The third approach is certificate authority pinning, where you pin an intermediate or root certificate authority certificate instead of your server certificate. This provides the most flexibility because you can change your server certificate freely as long as it changes to the pinned certificate authority. However, this offers weaker security because if that certificate authority is compromised, your protection is lost. Let me explain the decision flowchart. The process starts by asking whether you need maximum security. If yes, use full certificate PIN but be prepared for frequent app updates. If no, ask whether you control the certificate renewal process. If yes, use public key PIN, which is the sweet spot for most organizations. If no, ask whether you trust a specific certificate authority chain. If yes, use certificate authority PIN. If no, you should reconsider your requirements because pinning may create more operational problems than it solves. Implementation best practices. Let me share the critical best practices for implementing certificate pinning successfully, focusing on the complete lifecycle from development through ongoing maintenance. The sequence diagram shows the 4 phases of pinning implementation. In the setup phase, the developer extracts the certificate hash from the server certificate using tools like OpenSSL. The developer creates a pin config, which for mobile apps is source code and for desktop apps might be a configuration file. The developer must include at least 2 pins: the primary certificate and a backup certificate that has been generated but not yet deployed. The build system compiles everything into the app binary with the pins embedded. In the validation phase during runtime, the app binary connects to the server which presents its certificate. The app binary validates the certificate chain against the OS Trust Store. Then the app binary reads the embedded pins from its own compiled code and compares the certificate hash against these embedded values. If the comparison succeeds, the connection proceeds. In the reporting phase, if pin validation fails, the app binary should send a report to a report server. This report includes the expected pins, the actual certificate read, and the timestamp. This allows your security team to distinguish between attacks and configuration errors. In the rotation phase, which happens periodically, the developer generates new certificate pins and releases an app update containing both old and new pins. Users install this update. Only after sufficient adoption of the new app version should you deploy the new certificate to the server. Then in a subsequent app update, you remove the old pins. The code example shows a JSON configuration structure. The pins array contains objects with SHA-256 hashes and comments explaining each pin. The enforce mode field determines whether to block connections or just report. The report URI specifies where to send failure reports. The include subdomains field applies pins to all subdomains. This configuration would be compiled into your mobile app or bundled with your desktop application. Thank you for your attendance. Please consider subscribing to the channel and liking this video.